All right, hello everybody. Welcome back to the channel. My name is Michael, and I hope you're having a wonderful day so far. Today we're going to be jumping back into C Programming: A Modern Approach, second edition by K.N. King. We're going to be jumping into Chapter 7, Basic Types. So super excited to get started on this one and get some more information on, giving our variables some type definitions. This is from the live stream where I read the entire chapter live. If you'd like to join me, I stream myself learning computer science and programming almost every single day. Thanks so much for being here. Let's go ahead and get started. Chapter 7, Basic Types. Make no mistake about it, computers process numbers, not symbols. We measure our understanding and control by the extent to which we can arithmetize an activity. So far, we've used only two of C's basic built-in types, int and float. We've also seen underscore bool, which is a basic type in C99. This chapter describes the rest of the basic types and discusses important issues about types in general. Section 7.1 reveals the full range of integer types, which include long integers, short integers, and unsigned integers. Section 7.2 introduces the double and long double types, which provides a larger range of values and greater precision than float. Section 7.3 covers the char type, which we'll need in order to work with character data. Section 7.4 tackles the thorny topic of converting a value of one type to an equivalent value of another. Section 7.5 shows how to use typedef to define new type names. Finally, Section 7.6 describes the size of operator, which measures the amount of storage required for a type. 7.1 Integer Types. C supports two fundamental different kinds of numeric data, integer types and floating types. Values of an integer type are whole numbers, while values of floating type can have a fractional part as well. The integer type, in turn, are divided into two categories, signed and unsigned. Signed and unsigned integers. The leftmost bit of a signed integer, known as the sign bit, is 0 if the number is positive, or 0, 1 if it's negative. Thus, the largest 16-bit integer that has a binary representation, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, which has the value of this. The largest 32-bit integer is this, which has a value of this. An integer with no sign bit, the leftmost bit is considered part of the number's magnitude, is said to be unsigned. The largest 16-bit unsigned integer is this, and the largest 32-bit unsigned integer is this. By default, an integer variable are signed in C. The leftmost bit is reserved for the sign. To tell the compiler that a variable has no sign bit, we declare it to be unsigned. Unsigned numbers are primarily useful for system programming and low-level machine-dependent applications. We'll discuss typical applications for unsigned numbers in Chapter 20. Until then, we'll generally avoid them. C's integer types come into different sizes. The int type is usually 32 bits, but maybe 16 bits on older CPUs. Since some programs require numbers that are too large to store in int form, C also provides long integers. At times, we may need to conserve memory by instructing the compiler to store a number in less space than normal. Such a number would be called a short integer. To construct an integer type that exactly meets our needs, we can specify that a variable is long or short, signed or unsigned. We can even combine specifiers like long, unsigned, int. However, only the following 6 combinations actually produce different types: short int, unsigned short int, unsigned int, long int, unsigned long int. Other combinations are synonyms for one of these 6 types. For example, long signed int is the same as long int, since integers are always signed unless otherwise specified. Incidentally, the order of the specifiers doesn't matter. Unsigned short int is the same as short unsigned int. C allows us to abbreviate the names of integer types by dropping the word int. For example, unsigned short int may be abbreviated to unsigned short, and long int may be abbreviated to just long. Omitting int is a widespread practice among C programmers, and some newer C-based languages, including Java, actually require the programmer to write short or long rather than short int or long int. For these reasons, I'll often omit the word int when it's not strictly necessary. The range of values represented by each of the 6 integer types varies from one machine to another. However, there are a couple of rules that all compilers must obey. First, the C standard requires that short int, int, and long int each cover a certain minimum range of values. See section 23.2 for details. Second, the standard requires that int not be shorter than short int and long int not be shorter than int. However, it's possible that short int represents the same range of values as int. Also, int may have the same range as long int. Table 7.1 shows the usual range of values for the integer types on a 16-bit machine. Note that short int and int have identical ranges. Table 7.2 shows the usual ranges on a 32-bit machine. Here, int and long int have identical ranges. In recent years, 64-bit CPUs have become more common. Table 7.3 shows typical ranges for the integer types on a 64-bit machine, especially under Unix. Once more, let me emphasize that the range shown in Table 7.1, 7.2, and 7.3 aren't mandated by the C standard and may vary from one compiler to another. One way to determine the ranges of the integer types from a particular implementation is to check the limits.h header, which is part of the standard library. This header defines macros that represent the smallest and largest values of each integer type. Integer types in C99. C99 provides two additional standard types, long int and unsigned long int. These types were added because of the growing need for very large integers and the ability for newer processors to support 64-bit arithmetic. Both long types are required to be at least 64 bits wide, so the range of long int values is typically -2 to the power of 63, or this very large negative number. 2 to the power of 63 minus 1, or this very large unsigned number. And a range of unsigned long int values is usually from 0 to 2 to the power of 64 minus 1, this even larger unsigned int value. The short int, long int, and long int types, along with the unsigned char type, are called standard signed integer types in C99. The unsigned short int, unsigned long int, and unsigned long int types, along with the unsigned char type and the underscore bool type, are called standard unsigned integer types. In addition to the standard integer types, the C99 standard allows for implementation-defined extended integer types, both signed and unsigned. For example, a compiler might provide signed and unsigned 128-bit integer types. Integer constants. Let's turn our attention to constants, numbers that appear in the text of a program, not numbers that are read, written, or computed. C allows integer constants to be written in decimals base 10, octal base 8, or hexadecimal base 16. Octal and hexadecimal numbers. An octal number is written using only the digits 0 through 7. Each position in an octal number represents to a power of 8, just as each position in a decimal number represents to a power of 10. Thus, the octal number 237 represents the decimal number 2 times 8 to the power of 2 plus 3 times 8 to the power of 1 plus 7 times 8 to the power of 0, which is equal to 159. A hexadecimal or hex number is written using the digits 0 through 9 plus the letters A through F, which stands for 10 through 15, respectively. Each position in a hex number represents a power of 16. The hex number 1AF has the decimal value 1 times 16 squared plus 10 times 16 to the power of 1 plus 15 times 16 to the power of 0, which is equal to 431. Decimal constants contain digits between 0 and 9, but must not begin with a 0. Octal constants contain only digits between 0 and 7 and must begin with a 0. Hexadecimal constants contain digits between 0 and 9 and letters between A and F, and always begin with 0x. The letters in a hexadecimal constant may be either uppercase or lowercase. Keep in mind that octal and hexadecimals are nothing more than an alternative way of writing numbers. They have no effect on how the numbers are actually stored. Integers are always stored in binary regardless of what notation we've used to express them. We can switch from one notation to another at any time and even mix them. 10 plus 015 plus 0x20 has a value of 55 in decimal. Octal and hex are most convenient for writing low-level programs. We won't use these notations much until chapter 20. The type of a decimal integer constant is normally int. However, if the value of the constant is too large to store it as an int, the constant has a type long int instead. In the unlikely case that the constant is too large to store as a long int, the compiler will try unsigned long int as a last resort. The rules for determining the type of an octal or hexadecimal constant are slightly different. The compiler will go through the types int, unsigned int, long int, an unsigned long int, until it finds a more capable type of representing the constant. To force the compiler to treat a constant as a long integer, just follow it with the letter capital L or lowercase l. To indicate that a constant is unsigned, put the letter U, capital U, or U after it, right? Capital L and U may be used in combination to show that a constant is both long and unsigned. The order of the L and U doesn't matter, nor does their case. Integer constants in C99. In C99, integer constants that end with either LL or LL, the case of the two letters must match, have type long int. Adding the letter U or U before or after the double L's denote a constant of type unsigned long int. C99's general rule for determining the type of an integer constant are a bit different from those in C89. The type of a decimal constant with no suffix, capital U, capital L, lowercase l, double capital L, or double lowercase l, is the smallest of the types int, or long int that can be represent the value of the constant. For an octal or hexadecimal constant, however, the list of possible types is int, unsigned int, unsigned long int, long int, and unsigned long int, in that order. Any suffix at the end of the constant changes the list of possible types. For example, a constant that ends with the capital U or lowercase u for unsigned must have one of the types unsigned, int, unsigned long int, or unsigned long int. A decimal constant that ends with the capital L or lowercase l must have one of the types long int or long int. There's also a provision for a constant to have an extended integer type if it's too large to represent using one of the standard integer types. Integer overflow. When arithmetic operations are performed on integers, it's possible that the result will be too large to represent. For example, when an arithmetic operation is performed on two int values, the result must be able to be represented as an int. If the result can't be expressed as an int because it requires too many bits, we say that overflow has occurred. The behavior when integer overflow occurs depends on whether the operands are signed or unsigned. When overflow occurs during an operation on signed integers, the program behavior is undefined. Recall that section 4.4 that the consequences of undefined behavior may vary. Most likely the result of the operation will simply be wrong, and the program could crash or exhibit undesirable behavior. When overflow occurs during an operation on unsigned integers, positive values, though the result is defined, we get the correct answer modulo 2 to the power of n, where n is the number of bits used to store the result. For example, if we add 1 to the unsigned 16-bit number 65,535, the result is guaranteed to be 0. Reading and writing integers. Suppose that a program isn't working because one of its int variables is overflowing. Our first thought is to change the type of the variable from int to long int, but we're not done yet. We need to see how the changes will affect the rest of the program. In particular, we must check whether the variable is used in a call to printf or scanf. If so, the format string in the call will also need to be changed, since the %d conversion only works for the int type. Reading and writing unsigned short and long integers require several new conversion specifiers. When reading or writing an unsigned integer, use the letter U, O, or X instead of the D in the conversion specification. If the U specifier is present for unsigned integer, the number is read or written in decimal notation, O indicates octal notation, and X indicates hexadecimal notation. So if we have a variable U, which is an unsigned int, which is a positive integer, we read U in base 10, we can use the %u specifier. Conveniently, it's the same character as the variable definition, which is kind of annoying, but we can use the %u specifier here to write in base 10. Now you can read it in base 8 and then print it out in base 8. And same with base 16 with this x. So you can read it in as the value and save it into U. Okay, got you. When reading or writing a short integer, put the letter H in front of D, O, U, or X. Short S, scanf, %hd, %s. Printf, %hd, s. When reading or writing long integers, put the lowercase letter L in front of D, O, U, or X. Variable L here, which is of type long. They're going to save at the variable type in the variable long address the scanf for the long integer specifier here. and then print out the long integer specifier for the L variable. When reading or writing a long integer, C99 only, put the letters double L lowercase in front of DOU or X. So long double L for a double L is our variable definition or name. We're going to scanf the double LD, so the long decimal or like integer, into the long variable, and we're going to print that out. Okay, then we have a program here summing a series of numbers revisited. In section 6.1, we wrote a program that sums a series of integers entered by the user. One problem with this program is that the sum, or one of the input numbers, might exceed the largest value of an int variable. Here's what might happen if the program is run on a machine whose integers are 16 bits long. This program sums a series of integers. Enter integers 0 to terminate. 10,000, 20,000, 30,000, 0. The sum is -5536. The sum was 60,000, which wouldn't fit in an int variable, so overflow occurred. When overflow occurs with signed numbers, the outcome is undefined. In this case, we got an apparently meaningless number. To improve the program, let's switch to the long variable. Sums a series of numbers using long variables. We include the standard IO. We have int main void. We have a long n variable and sum 0. We make the prompt that we're going to print a series of numbers, and we're going to enter until we hit 0. We're going to run a while loop and scan in the input that they say within the while loop and add that to the sum variable. Once the loop terminates, when n becomes 0, we actually print out what the sum is. The change was fairly simple. We declared n and sum to be long variables instead of int variables, and then in our printf, we had to specify the long int specifier in the scanf and printf instead of just the %d. 7.2, floating types. The integer types aren't suitable for all applications. Sometimes we'll need variables that can store numbers with digits after the decimal point, or numbers that are exceedingly large or small. Numbers like these are stored in floating point format, so-called because the decimal point floats. C provides 3 floating types corresponding to different floating point formats: float, single precision float, double precision floating point, and long double extended precision floating point. Float is suitable when the amount of the precision isn't critical, calculating temperatures to 1 decimal point, for example. Double provides greater precision, enough for most programs. Long double, which supplies the ultimate in precision, is rarely used. The C standard doesn't state how much precision the float, double, and long double type provide, since different computers may store floating point numbers in different ways. Most modern computers follow the specifications in IEEE standard 754, also known as IEC 60559, so we'll just use it as an example. The IEEE floating point standard. IEEE standard 754, developed by the Institute of Electrical and Electronics Engineers, provides 2 primary formats for floating point numbers: single precision 32-bit and double precision 64-bit. Numbers are stored in a form of scientific notation, with each number having 3 parts: a sign, an exponent, and a fraction. The number of these bits reversed for the exponent determines how large or small numbers can be, while the number of bits in the fraction determines the precision. In single precision format, the exponent is 8 bits long, while the fraction occupies 23 bits. As a result, a single precision has a maximum value of approximately 3.4 times 10 to the power of 38, with a precision of about 6 decimal digits. The IEEE standard also describes 2 other formats: single extended precision and double extended precision. The standard doesn't specify the number of bits in these formats, although it requires that the single extended type occupy at least 43 bits and the double extended type at least 79 bits. For more information about the IEEE standard and floating point arithmetic in general, see Why Every Computer Scientist Should Know About Floating Point Arithmetic by David Goldberg back in March of '91. Table 7.4 shows the characteristics of the floating types when implemented according to the IEEE standard. The table shows the smallest positive normalized values. Subnormal numbers can be smaller. The long double type isn't shown in the table since its length varies from one machine to another, with 80 bits and 128 bits being the most common sizes. So for float, we have 1.17 times 10 to the power of negative 38 for the smallest, and the largest being 3.4 times 10 to the 38, with 6 digits of precision. And with a double float, we have 2.22507 times 10 to the power of negative 308, and for the largest value, we have 1.79769 times 10 to the power of 308, with 15 digits of precision. On computers that don't follow the IEEE standard, Table 7.4 won't be valid. In fact, some machines, float may have the same set of values as double, or double may have the same values as long double. Macros that define the characteristics of the floating types can be found in float.h header. In C99, the floating types are divided into two categories. The float, double, and long double types fall into one category called the real floating types. Floating types also include the complex types float underscore complex, double underscore complex, and long double underscore complex, which are new in C99. Floating constants. Floating constants can be written in a variety of ways. The following constant, for example, are a valid way of writing the number 57.0. 57.0, 57.0, 57.0E0, 57 capital E0, 5.7E1, 5.7E plus 1, 0.57E2, 570.E negative 1. As you can see, there's many different ways to write. A floating constant must contain a decimal point and or an exponent. The exponent indicates the power of 10 by which the number is to be scaled. If an exponent is present, it must be preceded by the letter capital E or lowercase e, and an optional plus or minus sign may appear after the capital E or lowercase e. By default, floating constants are stored as double precision numbers. In other words, when a C compiler finds the constant 57.0 in a program, it arranges for the number to be stored in memory in the same format as double variable. This rule generally causes no problem since double values are converted automatically to float when necessary. On occasion, it may be necessary to force the compiler to store a floating constant in float or a long double format to indicate that only single precision is desired. Put the letter capital F or lowercase f at the end of the constant. For example, 57.0 capital F to indicate that the constant should be stored in long double format. Put the letter capital L or lowercase l at the end. 57.0 L. C99 has a provision for writing floating constants in hexadecimal. Such a constant begins with 0x or 0 capital X. Like a hexadecimal integer constant, this feature is rarely used. Reading and writing floating point numbers. As we've discussed, the conversion specifications %e, %f, and %g are used for reading and writing single precision floating point numbers. Values of type double and long double require slightly different conversions. When reading a value of type double, put the letter L in front of E, F, or G. So you have double with the variable D. Scan F, we're going to read into the value of D a double float indicated by LF in this conversion specifier. Note, use L only in a scanf format string, not a printf string. In a printf format string, the E, F, and G conversions can be used to write either float or double values. C99 legalizes the use of L, E, LF, and LG in calls to printf, although the L has no effect. When reading or writing a value of type long double, put the letter capital L in front of the E, F, or G. So if you're reading long double for float values, right, you would use capital L in front of the conversion specifier. 7.3 Character types. The only remaining basic type is char, the character type. The values of type char can vary from one computer to another because different machines may have different underlying character sets. Character sets. Today's most popular character set is ASCII, American Standard Code for Information and Interchange, a 7-bit code capable of representing 128 characters. In ASCII, the digits are 0 to 9 are represented by the codes 0110000 through 0111001, and the uppercase letters capital A to Z are represented by 10000001 through 1011010. ASCII is often extended to a 256 character code known as Latin 1 that provides the characters necessary for Western European and many African languages. A variable of type char can be assigned any single character. Char, ch is equal to quote a, lowercase a, ch equals to uppercase a, ch equals to quote 0, ch can also equal a space. Notice that character constants are enclosed in single quotes, not double quotes. Operations on characters. Working with characters in C is simple because of the one fact: C treats characters as small integers. After all, characters are encoded in binary, and it doesn't take much imagination to view these binary codes as integers. In ASCII, for example, character codes range from 0000000 to 1111111, which we can think of as integers from 0 to 127. The character, quote, A, has a value of 97, quote, capital A has a value of 65, quote, 0 has a value of 48, and, quote, space has a value of 32. The connection between characters and integers in C is so strong that character constants actually have int type rather than char type. An interesting fact, but not one that will often matter to us. When a character appears in a computation, C simply uses its integer value. Consider the following examples, which assume the ASCII character set: char ch and int I, where we assign I to equal to, quote, A, I is now 97. ch is equal to 65, ch is now capital A. If we do ch is equal to ch plus 1, ch is now B. We move to the next letter, 66. We do ch plus plus to bring it to 67, which is now, quote, C, or capital C. Characters can be compared just as numbers can. The following if statement checks whether ch variable contains a lowercase letter. If so, it converts ch variable to uppercase. If, quote, A, lowercase, is less than or equal to ch, and ch is less than or equal to, quote, lowercase z, then we will make ch equal to ch less than lowercase a plus uppercase A to convert it to uppercase. Comparisons such as, quote, A less than or equal to ch are done using the integer values of the characters involved. These values depend on the character set in use, so programs that use less than or equal to, greater than, and greater than or equal to compare characters may not be portable. The fact that characters have the same properties as numbers has some advantages. For example, we can easily write a for statement whose control variable steps through all uppercase letters. For ch is equal to, quote, capital A, while ch is less than or equal to, quote, uppercase z, we will increase the character. On the other hand, treating characters as numbers can lead to various programming errors that won't be caught by the compiler and lets us write meaningless expressions such as, quote, lowercase a times, quote, lowercase b divided by, quote, lowercase c. It can also hamper portability since our program may be based on assumptions about the underlying character set. Our for loop, for example, assumes that the letters from capital A to capital Z have consecutive codes. Signed and unsigned characters. Since C allows characters to be used as integers, it shouldn't be surprising that the char type, like the integer types, exist in both signed and unsigned versions. Signed characters normally have values between -128 and 127, while unsigned characters have values between 0 and 255. The C standard doesn't specify whether ordinary char is a signed or an unsigned type. Some compilers treat it as a signed type, while others treat it as an unsigned type. Some even allow the programmer to select via a compiler option whether char should be a signed or unsigned. Most of the time, we don't really care whether char is signed or unsigned. Once in a while, though, we do, especially if we're using a character variable to store a small integer. For this reason, C allows the use of the words signed and unsigned to modify char. Signed char, SCH, and unsigned char is UCH. Portability tip: don't assume that char is either signed or unsigned by default. If it matters, use signed char or unsigned char instead of just char. In light of the close relationship between character and integers, C89 uses the term internal types to refer to both the integer types and the character types. Enumerated types are also integral types. C99 doesn't use the term integral types. Instead, it expands the meaning of the integer types to include the character types and the enumerated types. C99's _bool type is considered to be an unsigned integer type. Arithmetic types. The integer types and floating types are collectively known as arithmetic types. Here's a summary of the arithmetic types in C89, divided into categories and subcategories. Integral types: char, signed integer types for signed char, short int, long int. Unsigned integer types: unsigned char, unsigned short int, unsigned int, and unsigned long int. Enumerated types are also in the integral types. Floating types: float, double, long double. C99 has more complicated hierarchy for its arithmetic types. Integer types: char, signed integer types, both standard, signed char, short int, long int, and extended. Unsigned integer types, both standard, unsigned char, unsigned short int, unsigned long int, unsigned long int, and underscore bool and extended in the enumerated types, where also floating types in C99 are real floating types such as float, double, and long double, and complex types such as float underscore complex, double underscore complex, and long double underscore complex. Escape sequences. A character constant is usually one character enclosed in single quotes, as we've seen in previous examples. However, certain special characters, including the new line character, can't be written in this way because they're invisible, non-printing, or because they can't be entered from the keyboard. So that programs can deal with every character in the underlying character set, C provides a special notation, the escape sequence. There are two kinds of escape sequences: character escapes and numeric escapes. We saw a partial list of character escapes in section 3.1. Table 7.5 gives the complete set here, where we have \A is alert, \B is backspace, F is form feed, N is new line, R is carriage return, T is horizontal tab, V is vertical tab, \\, is backslash, question mark is question mark, single quote is single quote, and double quote is double quote. The \A, B, F, R, T, and V escapes represent common ASCII control characters. The \N escape represents the ASCII line feed character. The \\, escape allows a character constant or string to contain the \/ character. The \, single quote escape allows a character constant to contain the single character, and while the \, double quote escape allows a string to contain the double quote character. The \, question mark escape is rarely used. Character escapes are handy, but they have a problem. The list of character escapes doesn't include all of the non-printing ASCII characters, just the most common. Character escapes are also useless for representing characters beyond the basic 128 ASCII characters. Numeric escapes, which can represent any character, are the solution to this problem. To write a numeric escape for a particular character, first look up the character's octal or hexadecimal value in a table like the one in Appendix E. For example, the ASCII escape character, decimal value 27, has the value 33 in octal and 1B in hex. Either of these codes can be used to write an escape sequence. An octal escape sequence consists of the \/ character followed by an octal number with at most 3 digits. This number must be representable as an unsigned character, so its maximum value is normally 377 octal. For example, the escape character could be written as \33 or \033. Octal numbers in escape sequences, unlike octal constants, don't have to begin with 0. A hexadecimal escape sequence consists of \x followed by a hexadecimal number. Although C places no limit on the number of digits in a hexadecimal number, it must be representable as an unsigned character. Hence, it can't exceed F if characters are 8 bits long. Using this notation, the escape character would be written in \1b or \1 uppercase b. The x must be in lowercase, but the hex digit, such as the lowercase b, can be both upper or lowercase. When used as a character constant, an escape sequence must be enclosed in single quotes. For example, a constant representing the escape character would be written as quote \33 or quote \x1 lowercase b. Escape sequences tend to get a bit cryptic, so it's often a good idea to give them names using the #define. #define escape as quote \33. Escape sequences can be embedded in strings as well, as we saw in section 3.1. Escape sequences aren't the only special notations for representing characters. Trigraph sequences provide a way to represent the characters #, bracket, / bracket, caret, curly brace, bar, curly brace, and tilde, which may not be available on keyboards in some countries. C99 adds universal character names, which resemble escape sequences. Unlike escape sequences, however, universal character names are allowed in identifiers. Character handling functions. Earlier in this section, we saw how to write an if statement that converts a lowercase character to uppercase. If the lowercase a is less than or equal to the character, and the character is less than or equal to lowercase z, then we're going to take the character, reduce it by the lowercase a, and add uppercase A to force it to be uppercase. This isn't the best method though. A faster and more portable way to convert case is to call C's toUpper library function. C equals toUpper on the character, converts the character to uppercase. When it's called, toUpper checks whether its argument character, in this case, is a lowercase character. If so, it returns the corresponding uppercase letter. Otherwise, toUpper returns the value of the argument. In our example, we've used the assignment operator to store the return value of toUpper back into the ch variable. Although we could just as easily have done something else with it, stored it in another variable, say, or have tested it in an if statement. If toUpper character is equal to uppercase A, ... Programs that call toUpper need to have the following include directive at the top: include C type.h. toUpper isn't the only useful character handling function in C library. Section 23.5 describes them all and gives examples of their use. Reading and writing characters using scanf and printf. The %C conversion specification allows scanf and printf to read and write single characters. Char, ch, defined, will scanf %C to read in a character and save that in char, and then print out the character, writes a single character. Scanf doesn't skip whitespace characters before reading a character. If the next unread character is a space, then the variable ch in the previous example will contain a space after scanf returns. To force scanf to skip whitespace before reading character, put a space in front of its format string just before the %C. Scanf with a space just before the %C to specify that spaces are allowed. It will be skip the white spaces, then read ch. Recall that section 3.2 that blank in scanf format string means skip 0 or more whitespace characters. Since scanf doesn't normally skip whitespace, it's easy to detect the end of an input line. Check to see if the character just read is the new line character. For example, the following loop will read and ignore all remaining characters in the current input line. Do scanf while the character is not a \n. When scanf is called the next time, it will read the first character on the next input line. Reading and writing characters using getchar and putchar. C provides other ways to read and write single characters. In particular, we can use the getchar and putchar functions instead of calling scanf and printf. Putchar writes a single character. Putchar char. Each time getchar gets called, it reads one character, which it returns. In order to save this character, we must use assignment to store it in a variable. Getchar, for every char, reads a character and stores it into ch. Getchar usually returns an int value rather than a char value. The reason will be discussed in later chapters. As a result, it's not unusual for a variable to have type int rather than char if it will be used to store a character read by getchar. Like scanf, getchar doesn't skip whitespace characters as it reads. Using getchar and putchar rather than scanf and printf saves time when a program is executed. Getchar and putchar are fast for two reasons. First, they're much simpler than scanf and printf, which are designed to read and write many kinds of data in a variety of formats. Second, getchar and putchar are usually implemented as macros for additional speed. Getchar has another advantage over scanf because it returns the character that it reads. Getchar lends itself to various C idioms, including loops that search for a character or skip over all occurrences of a character. Consider the scanf loop we used to skip the rest of an input line. Do scanf for a character, and we'll save that in the char variable while the char is not equal to \n. Rewriting this loop using getchar gives us the following. Do char getchar while the ch is not equal to the \n. Moving the call of getchar into the controlling expression allows us to condense the loop while into this. This loop reads a character, stores it into the variable ch, then tests if the ch is not equal to the new line character. If the test is successful, the loop body, which is empty, is executed. Then the loop test is performed once more, causing a new character to be read. Actually, we don't even need the character variable. We can just compare the return value of getchar with the new line character. The resulting loop is a well-known C idiom that's cryptic but worth learning. Getchar is useful in loops that skip characters as well as loops that search for characters. Consider the following statement which uses the getChar to skip an indefinite number of blank characters, while the char is equal to getChar, and that is equal to a blank space character, skips blank characters. When the loop terminates, ch will contain the first non-blank character that getChar encountered. Be careful if you mix together getChar and scanf in the same program. Scanf has a tendency to leave behind characters that it has peeked at but not read, including the new line character. Consider what happens if we try to read a number first, then a character. So we call printf and we are going to say enter an integer for a prompt. We're going to scanf and read that integer into a variable I. We're going to print, then enter a command, and we're going to have the command equal to getChar. The call of scanf will leave behind any characters that weren't consumed during the reading of I, including but not limited to the new line character. getChar will fetch the first leftover character, which wasn't what we had in mind. 7.4 Type conversions. Computers tend to be more restrictive than C when it comes to arithmetic. For a computer to perform an arithmetic operation, the operands usually must be of the same size, the same number of bits, and be stored in the same way. A computer may be able to add two 16-bit integers directly, but not a 16-bit integer and a 32-bit integer, or a 32-bit integer and a 32-bit floating point number. C, on the other hand, allows the basic types to be mixed in expressions. We can combine integers, floating point numbers, and even characters in a single expression. The C compiler may then even have to generate instructions that convert some operands to a different type so that the hardware will be able to evaluate the expression. If we add a 16-bit short and a 32-bit int, for example, the compiler will arrange the short value to be converted to 32 bits. If we add an int and a float, the compiler will arrange for the int to be converted to a float format. This conversion is a little more complicated since int and float values are stored in different ways. Because the compiler handles these versions automatically, without the programmer's involvement, they're known as implicit conversions. C allows the programmer to perform explicit conversions using the cast operator. I'll discuss implicit conversions first, postponing explicit conversions until later in this section. Unfortunately, the rules for performing implicit conversions are somewhat complex, primarily because C has so many different arithmetic types. Implicit conversions are performed in the following situations: when the operands in an arithmetic or logical expression don't have the same type. C performs what are known as usual arithmetic conversions. When the type of the expression on the right side of an assignment doesn't match the type of the variable on the left. When the type of an argument in a function call doesn't match the type of the corresponding parameter. When the type of an expression in a return statement doesn't match the function's return type. We'll discuss the first two cases now and save the others for Chapter 9. The usual arithmetic conversions. The usual arithmetic conversions are applied to the operands of most binary operators, including the arithmetic, relational, and equality operators. For example, let's say that f has a type float and I has a type int. The usual arithmetic conversions will be applied to the operands in the expression f plus I because their types aren't the same. Clearly, it's safer to convert I to type float, matching f's type, rather than to convert f to type int, matching i's type. An integer can always be converted to a float. The worst that can happen is a minor loss of precision. Converting a floating point number to an int, on the other hand, would cost us the fractional part of the number. Worse still, we'd get a completely meaningless result if the original number were larger than the largest possible integer or smaller than the smallest possible integer. The strategy behind the usual arithmetic conversions is to convert operands to the narrowest type that will safely accommodate both values. Roughly speaking, one type is narrower than another if it requires fewer bytes to store. These types of operands can often be made to match by converting the operand of the narrower type to the type of the other operand. This act is known as promotion. Among the most common promotions are the integral promotions, which convert a character or short integer to type int or to unsigned int in some cases. We can divide the rules for performing the usual arithmetic conversions into two cases. The types of either operand is a floating type. Use the following diagram to promote the operand whose type is narrower. Floats promote to doubles, doubles promote to long doubles. That is, if one operand has type long double, then convert the other operand to type long double. Otherwise, if one operand has a type double, convert the other operand to type double. Otherwise, if one operand has a type float, convert the other operand to type float. Note that these rules cover mixtures of integer and floating types. If one operand has type long int, for example, and the other has type double, the long int operand is converted to double. Neither operand type is a floating type. First, perform integral promotion on both operands, guaranteeing that neither operand will be a character or short integer. Then use the following diagram to promote the operand whose type is narrower. Int gets promoted to unsigned int. Unsigned int is promoted to long int, and long int is promoted to unsigned long int. There's one special case, but it occurs only when long int and unsigned int have the same length, 32 bits say. Under these circumstances, if one operand has type long int and the other has type unsigned int, both are converted to unsigned long int. When a signed operand is combined with an unsigned operand, the signed operand is converted to an unsigned value. The conversion involves adding or subtracting a multiple of n plus 1, where n is the largest representable value of the unsigned type. This rule can cause obscure programming errors. Suppose that the int variable I has the value of -10, and the unsigned int variable u has the value of +10. If we compare I and u using the less than operator, we might expect to get the result 1 true. Before the comparison, however, I is converted to unsigned int, since a negative number can't be represented as an unsigned integer. The converted value won't be -10, instead the value of this is added, assuming that this is the largest unsigned int value, giving a converted value of this. The comparison I less than u will therefore produce 0. Some compilers produce a warning message such as comparison between signed and unsigned, when a programmer attempts to compare a signed number with an unsigned number. Because of traps like this one, it's best to use unsigned integers as little as possible, and especially never mix them with signed integers. The following example shows the usual arithmetic conversions in action. We have char c, short int s, int I, unsigned int u, long int l, unsigned long int ul, a float f, double d, long double ld. We have I is equal to I plus c, where I is an int. We're taking I and adding the char value to it. C is converted to an int. Conversion during assignment. The usual arithmetic conversions don't apply to assignment. Instead, C follows the simple rule that the expression on the right side of the assignment is converted to the type of the variable on the left side. If the variable's type is at least as wide as the expressions, this will work without a snag. For example, we have char c, int I, float f, and double d. I equals to c. C is converted to an int. I has narrower scope than float, so integers have narrower scope than floats, and then doubles obviously have larger scope than the float values. Other cases are problematic. Assigning a floating point number to an integer variable drops the fractional part of the number. We lose the 0.97 altogether. Moreover, assigning a value to a variable of a narrow type will give a meaningless result. Or worse, if the value is outside the range of the variable's type. C equals 10,000, wrong. I is equal to 1.0 E20, wrong. And F equals 1.0 E100, wrong. A narrowing assignment may elicit a warning from the compiler or from tools such as lint. It's a good idea to append the F suffix to a floating point constant if it will be assigned to a float variable, as we've been doing since chapter 2. Without the suffix, the constant 3.14159 would have type double, possibly causing a warning message. In C99, implicit conversions in C99. The rules for implicit conversions in C99 are somewhat different from the rules in C89, primarily because C99 has additional types of underscore bool, long types, and extended integer types and complex types. For the purpose of defining conversion rules, C99 gives each integer type an integer conversion rank. Here are the ranks from highest to lowest. 1. Long int, unsigned long int. 2, long int, unsigned long int, 3, int, unsigned int, 4, short int, unsigned short int, 5, char, signed char, unsigned char, and 6, bool. For simplicity, I'm ignoring extended integer types and enumerated types. In place of C89's integral promotions, C99 has integer promotions, which involve converting any type whose rank is less than int and unsigned int to int, provided that all values of the type can be represented using int, or else to unsigned int. As in C89, the C99 rules for performing the usual arithmetic conversions can be divided into two cases. The type of either operand is a floating type. As long as neither operand has a complex type, the rules are the same as before. The conversion rules for complex types will be discussed in sections 27.3. Neither operand type is a floating type. First, perform integer promotion on both operands. If the types of the two operands are now the same, the process ends. Otherwise, use the following rules, stopping at the first one that applies. If both operands have signed types or both have unsigned types, convert the operand whose type has lesser integer conversion rank to the type of the operand with greater rank. If the unsigned operand has rank greater or equal to the rank of the type of signed operand, convert the signed operand to the type of the unsigned operand. If the type of the signed operand can represent all the values of the type of the unsigned operand, convert the unsigned operand to the type of the signed operand. Otherwise, convert both operands to the unsigned type corresponding to the type of the assigned operand. Incidentally, all arithmetic types can be converted to the _bool type. The result of the conversion is 0 if the original value is 0. Otherwise, the result is 1. Casting here. Although C's implicit conversions are convenient, we sometimes need a greater degree of control over type conversions. For this reason, C provides casts. A cast expression has the form type name expression. Type name specifies the type to which the expression should be converted. The following example shows how to use a cast expression to compute the fraction part of a float value. Float f, frac part. Frac part equals to f minus int f. The cast expression int f represents the result of the converting the value of f to type int. C's usual arithmetic conversions then require that int f be converted back to type float before the subtraction can be performed. The difference between f and int f is the fractional part of f, which was dropped during the cast. Int f is converted to an int. They also enable us to overrule the compiler and force it to do conversions that we want. Consider the following example. Float quotient, int dividend, and divisor. Quotient equals the dividend divided by the divisor. As it's now written, the result of the division, an integer, will be converted to float form before being stored in quotient. We probably want dividend and divisor converted to float before the division, though, so that we can get a more exact answer. A cast expression will do the trick. Float dividend divided by divisor. Divisor doesn't need to cast, since casting dividend to float forces the compiler to convert divisor to float also. Incidentally, C regards type name as a unary operator. Unary operators have high precedence than binary operators, so the compiler interprets float dividend divided by divisor as the float of the dividend first divided by the divisor. If you find this confusing, note that there are other ways to accomplish the same effect, such as quotient equals dividend divided by the cast of float on the divisor, or quotient equals to where you specify both of them. Casts are sometimes necessary to avoid overflow. Consider the following example. We have long I, and we have an int j, which is equal to 1,000. We times j by j, so we square j, and save that into long I. Overflow may occur. At first glance, this statement looks fine. The values of j times j is 1 million, and I is long, so it can easily store this value of this size, right? The problem is that when two int values are multiplied, the result will have type int. But j times j is too large to represent as an int on some machines, causing an overflow. Fortunately, using a cast avoids this problem. Since the cast operator takes precedence over the star, the first j is converted to long type forcing the second j to be converted to long as well. Note that the statement long j times j is wrong. This would not work since the overflow would already have occurred by the time the cast took place. 7.5 Type definitions. In section 5.2, we used the hashtag define directive to create a macro that would be used as a Boolean type. Hashtag define, capital BOOL, as int. There's a better way to set up a Boolean type, though, using a feature known as type definition. Type def int bool. Notice that the name of the type being defined comes last. Also, that I've capitalized the word bool. Capitalizing the first letter of a type name isn't required, it's just a convention that C programmers employ. Using type def to define bool causes the compiler to add bool to the list of type names that it recognizes. Bool can now be used in the same way as the built-in type names in variable declarations, cast expressions, and elsewhere. For example, we might use bool to declare variables, bool flag, same as int flag. The compiler treats bool as a synonym for int, thus flag is really nothing more than an ordinary int variable. Advantages of type definitions. Type definitions can make a program more understandable, assuming that the programmer has been careful to choose meaningful type names. For example, suppose that the variable names cash in and cash out will be used to store dollar amounts. Declaring dollars, capital D, as type def float dollars than writing dollars cash in, cash out is more informative than just writing float cash in, cash out. Type definitions can also make a program easier to modify. If we later decide that dollars should really be defined as double, all we need to do is change the type definition. The declaration of dollars variables need not be changed. Without the type definition, we would need to locate all the float variables that store dollar amounts, not necessarily an easy task, and change their declarations. Type definitions and portability. Type definitions are an important tool for writing portable programs. One of the many problems with moving a program from one computer to another is that types may have different ranges on different machines. If I is an integer variable, an assignment like I equals to 100,000 is fine on a machine with 32-bit integers, but will fail on a machine with 16-bit integers. For greater portability, consider using type def to define names for integer types. Suppose that we're writing a program that needs a variable capable of storing a product quantity in the range of 0 to 50,000. We could use long variables for this purpose, since they're guaranteed to be able to hold numbers up to at least this large number. But we'd rather use int variables, since arithmetic on int values may be faster than operations on long values. Also, int variables may take up less space. Instead of using the int type to declare quantity variables, we can define our own quantity type. Type def int quantity, and use this type to declare variables, quantity q. When we transport the program to a machine with shorter integers, we'll change the definition of quantity. Type def long quantity. This technique doesn't solve all our problems, unfortunately, since changing the definition of quantity may affect the way quantity variables are used. At the very least, calls to printf and scanf that use quantity variables will need to be changed, with %d conversion specifications replaced by %ld. The C library itself uses typedef to create names for types that can vary from one C implementation to another. These types often have names that end with _t, such as ptrdiff_t, size_t, and wchar_t. The exact definitions of these types will vary, but there are some typical examples. Typedef long int ptrdiff_t, typedef unsigned long int size_t, typedef int wchar_t. In C99, the standard int.h header uses typedef to define names for integer types with a particular number of bits. For example, int32_t is a signed integer type with exactly 32 bits. Using these types is an effective way to make programs more portable. 7.6, the size of operator. The size of operator allows a program to determine how much memory is required to store values of a particular type. The value of the expression size of type name is an unsigned integer representing the number of bytes required to store a value belonging to type name. Size of char is always 1, but the sizes of other types may vary. On a 32-bit machine, size of int is normally 4. Note that size of is a rather unusual operator since the compiler itself can't usually determine the value of a size of expression. The size of operator can also be applied to constants, variables, and expressions in general. If I and j are int variables, then size of I is 4 on a 32-bit machine, as is size of I plus j, right? When applied to an expression as opposed to a type, size of doesn't require parentheses. We could write size of I instead of size of I. However, parentheses may be needed anyways because of operator precedence. The compiler would interpret size of I plus j as size of I, then plus j. Because size of a unary operator takes precedence over the binary plus operator, to avoid problems, I always use parentheses in size of expressions. Printing a size of value requires care because the type of a size of expression is an implementation defined type named size underscore t. In C89, it's best to convert the value of the expression to a known type before printing it. Size underscore t is guaranteed to be an unsigned integer type, so it's safest to cast a size of expression to an unsigned long, the largest of C89's unsigned types, and then print it using the LU conversion. Printf size of int LU \n unsigned long size of int. In C99, the size t type can be larger than unsigned long. However, the printf function in C99 is capable of displaying size underscore t values directly without the need of casting. The trick is to use the letter z in the conversion specification followed by one of the usual integer codes, typically u. Printf size of int zu, given the size of the int. In C99 only. Question. Section 7.1 says that %o and %x are used to write unsigned integers in octal and hex notation. How do I write ordinary signed integers in octal or hex? You can use %o and %x to print a signed integer as long as its value isn't negative. These conversions cause printf to treat a signed integer as though it were unsigned. In other words, printf will assume the signed bit is part of the number's magnitude, as long as the signed bit is 0. There's no problem. If the signed bit is 1, printf will print an unexpectedly large number. Question, but what if the number is negative? How can I write it in octal or hex? There's no direct way to print a negative number in octal or hex. Fortunately, the need to do this is pretty rare. You can, of course, test whether the number is negative and print a minus sign yourself. Why are floating point constants stored in double form rather than float form? For historical reasons, C gives preference to the double type. Float is treated as a second-class citizen. Consider, for instance, the discussion of float in Kernighan and Ritchie's The C programming language. The main reason for using float is to save storage in large arrays, or less often to save time on machines where double precision arithmetic is particularly expensive. C originally mandated that all floating point arithmetic be done in double precision. C89 and C99 have no such requirement. Question. What do hexadecimal floating point constants look like, and what are they good for? A hexadecimal floating point constant begins with 0x, or 0 capital X, and must contain an exponent, which is preceded by the letter p, or lowercase p. The exponent may have a sign, and the constant may end with F, L, or capital L. The exponent is expressed in decimal, but represents by a power of 2, not a power of 10. For example, 0x1 dot BP3 represents the number 1.6875 times 10 to the power of 3, which is equal to 13.5. The hex digit B corresponds to the bit pattern 1011. The B occurs to the right of the period, so each one bit represents a negative power of 2. Summing these powers of 2 times 2 to the power of negative 1 plus 2 to the power of negative 3 plus 2 to the power of negative 4 yields 0.675. Hexadecimal floating point constants are primarily useful for specifying constants that require great precision, including mathematical constants such as e and pi. Hex numbers have a precise binary representation, whereas a constant written in decimal may be subject to a tiny rounding error when converted to binary. Hexadecimal numbers are also useful for defining constants with extreme values, such as values of the macros in float.h header. These constants are easy to write in hex, but difficult to write in decimal. Why do we use %lf to read double values, but %f to print it? This is a tough question to answer. First, notice that scanf and printf are unusual functions in that they aren't restricted to a fixed number of arguments. We say that scanf and printf have variable length argument lists. When functions with variable length argument lists are called, the compiler arranges for float arguments to be converted automatically to type double. As a result, printf can't distinguish between float and double arguments. This explains why %f works for both float and double arguments in calls to printf. Scanf, on the other hand, is passed a pointer to a variable. %f tells scanf to store a float value at that address passed to it, while %lf tells scanf to store a double value at that address. The distinction between float and double is crucial here. If given the wrong conversion specification, scanf will likely store the wrong number of bytes, not to mention the fact that the bit pattern for a float isn't the same as that for a double. Question: what's the proper way to pronounce char? There's no universally accepted pronunciation. Some people pronounce char in the same way as the first syllable of character. Others say char as in char-broiled. When does it matter whether a character variable is signed or unsigned? If we store only 7-bit characters in the variable, it doesn't matter since the signed bit will be 0. If we plan to store 8-bit characters, however, we will probably want the variable to have unsigned char type. Consider the following example. ch is equal to \xdb. If ch has been declared to have type char, the compiler may choose to treat it as a signed character. Many compilers do. As long as ch is used only as a character, there won't be any problem, but if ch is ever used in context that requires the compiler to convert its value to an integer, we're likely to have trouble. The resulting integer will be negative since ch's sign bit is 1. Here's another situation. In some kinds of programs, it's customary to use a char variable to store 1-byte integers. If we're writing such a program, we'll have to decide whether each variable should be signed char or unsigned char, just as we might decide whether ordinary integer variable should have type int or unsigned int. Question: I don't understand how the new line character can be the ASCII line feed character. When a user enters input and presses the enter key, doesn't that program read this as a carriage return character or carriage return plus a line feed? Answer: nope. As part of C's Unix heritage, it always regards the end of a line as being marked by a single line feed character. In Unix text files, a single line feed character, but no carriage return, appears at the end of each line. The C library takes care of translating the user's key press into a line feed character. When a program reads from a file, the IO library translates the file end of line marker, whatever it may be, into a single line feed character. The same transformations occur in reverse when output is written to the screen or to a file. See sections 22.1 for details. Although these translations may seem confusing, they serve an important purpose, insulating programs from details that may vary from one operating system to another. What's the purpose of the \? Escape sequence? The \? Escape is related to trigraph sequences which begin with ? If you should put ? in a string, there's a possibility the compiler will mistake it for the beginning of a trigraph. Replacing the second question mark by a \? Fixes the problem. Question: if getchar is faster, why would we ever use scanf to read individual characters? Although it's not as fast as getchar, the scanf function is more flexible. As we saw previously, the %c format string causes scanf to read the next input character. Space %c causes it to read the next non-white space character. Also, scanf is good at reading characters that are mixed in with other kinds of data. Let's say that our input data consists of an integer, then a single non-numeric character, then another integer. By using the format string %d, %c, %d, we can get scanf to read all 3 items. Question: under what circumstances do the integral promotions convert a character or short integer to an unsigned int? The integral promotions yield an unsigned int if the int type isn't large enough to include all possible values of the original type. Since characters are usually 8 bits long, or 1 byte, they are almost always converted to int, which is guaranteed to be at least 16 bits long. Signed short integers can always be converted to int as well. unsigned short integers are problematic. If short integers have the same length as ordinary integers, as they do on a 16-bit machine, then unsigned short integers will have to be converted to unsigned int. Since the largest unsigned short integer, 65,535 on a 16-bit machine, is larger than the largest int, 32,767. Question: exactly what happens if I assign a value to a variable that's not large enough to hold it? Roughly speaking, if the value is of an integral type and the variable is of an unsigned type, the extra bits are thrown away. If the variable has a signed type, the result is implementation defined. Assigning a floating point number to a variable, integer or floating, that's too small to hold it produces undefined behavior. Anything can happen, including program termination. Question: why does C bother to provide type definitions? Isn't defining a bool macro just as good as defining a bool type using typedef? There are two important differences between type definitions and macro definitions. First, type definitions are more powerful than macro definitions. In particular, array and pointer types can't be defined as macros. Suppose that we try to use a macro to define a pointer to integer type. Define ptr to int star. The declaration ptr to int pqr will become int star pqr. After pre-processing, unfortunately, only p is a pointer, q and r are ordinary integers. Type definitions don't have this problem. Second, typedef names are subject to the same scope rules as variables. A typedef name defined inside a function body wouldn't be recognized outside of the function. Macro names, on the other hand, are replaced by the preprocessor wherever they appear. You can say that compilers can usually determine the value of a size of expression. Can't a compiler always determine the value of a size of expression? In C89, yes. In C99, however, there's one exception. The compiler can't determine the size of a variable length array, because the number of elements in the array may change during the execution of the program. Alright, you guys, thanks so much for joining me. I appreciate you guys being here. That was Chapter 7, Basic Types from C Programming, a Modern Approach, 2nd edition by K.N. King. Thank you guys so much for being here and joining me. This was awesome reading Chapter 7, and I can't wait to get into Chapter 8 with you guys. Alright, peace.